In Module 3C, we will be studying the chain rule and partial derivatives. And in this video, we're going to focus on the first part, chain rule, which is used to determine the derivative of a composite function. Composite functions, remember, we've seen a couple of different notations. Essentially, if you can identify a function within a function, that is what we call a composite function. One way we can also write that is using the circle notation, which is equivalent to the notation or to this notation over here, g of h of x. All right, and so what the chain rule says is if I want to determine the derivative, all I need to do is, and Leibniz notation is a little cumbersome, but essentially all you do is take the derivative of the outside function, g, leave the inside function alone, and then once you're done with computing the derivative of g, then you multiply by the derivative of the inside part, h of x. And Leibniz notation, it's essentially the same thing. The only thing is we have to remember to evaluate the derivative of g with respect to x at h of x, meaning you input h of x into the derivative. Alright, and so really what we see, the way I think of this when I do chain rule is it's the derivative of the outer, g, this part, times the derivative of the inner, h. Okay, and if that helps you, great. If not, that's just one way, that's how I remembered it. And so here I have a natural log function, and technically when we study natural logs derivatives as well as exponential derivatives, we actually more or less defined the derivative using the chain rule. Okay, but let's go through and identify our g and our h using different colors. So our outside function, outside of the parentheses, is just natural log. So it'll be natural log is my outside function, and my inside function is whatever I have left over inside the set of parentheses. So that's x squared minus 3x plus 5. Alright, and so now I just follow the chain rule, or really what we said was the derivative of the natural log, and say that the derivative, f prime, is equal to 1 over the inside part, x squared, minus 3x plus 5. And multiply that with the derivative of the inside part, the x squared plus 3x plus 5. And that derivative is just 2x minus 3, using the power rule. Okay? And so right here we only had two composite functions, and we may need to actually use a chain rule repeatedly. So just continue the process, continue multiplying by the derivative of the inside function is for as many inside functions as you have. Another way I like to think of the chain rule is whenever you hit a set of parentheses, that's where you have to add a multiplication sign. So after you do the derivative, so do the derivative of the outside until you hit the parentheses, have a multiply. Do the derivative of the inside until you hit a set of parentheses, and then you have to multiply. Alright, and so in this function, it's a little bit more complex than what we saw before, but we can still find the derivative. And so if I identify the different chains I'm going to have, well, I'm going to have the one outside, the cubic, so that'll be my first one. And then on the inside, I'll have cosine, and I hit a set of parentheses, so that's where I'm going to have my next chain. And then the denominator, that there's no composition there, so that's just x squared e to the x plus 1. And so then my third chain is when I take the derivative of cosine, I'm going to need to multiply by the derivative of 1 minus x. Alright, so let's go ahead and do this. And oftentimes that's what you need to do, is just do it and find the chains as you go. So if I compute the derivative, this is equal to, doing the first stage, I have to do a 3 multiply by, and then the red, I just think of the red as an x, and so I leave that, and that becomes a square. Recopy whatever's inside. So this is cosine 1 minus x, and then x squared e to the x plus 1. Alright, and then now I'm done with the red. Go on to the next stage in blue, and that's a multiply. Okay. Next stage in blue, okay, this is a quotient, so I do the quotient rule. So I have, let's see, I have low, x squared e to the x plus 1, d high, which is a minus sign. And now I'm taking the derivative of cosine, so I have to multiply by the derivative of 1 minus x, which is just times a minus 1. And my third chain is now done. And then now let's see, I have to subtract from that minus high, so cosine 1 minus x times the derivative of this, and that's a product rule, so that's 1d2, so x squared e to the x plus 2x e to the x, and then that is all over the low squared. Okay, and this is done enough. So I wouldn't go any further because it's just the algebra gets to be insanely complicated, and it's not even worth it uh, to go through all that work to try and simplify this usually. Um, but the key point is that chain, our third chain, was right here. Okay, so you don't necessarily need three different things being all multiplied together. It could appear somewhere within the derivative that you're currently doing. Okay. Last thing is, oftentimes in this section in Module 3C, we will be focusing on applied problems. And so here we have an example where we have an oil tanker that's spilling oil in a circular pattern. The radius is given at time t or at time t minutes as this. How fast is the area of the spill increasing at 3 minutes? Well, we know that the area of a circle, since it's in a circular pattern, is just pi r squared. Okay, but it's asking for area, and it's giving me a time to determine the rate of change, how fast the rate of change in the area at a certain time. So I need to put in my radius function. So I have pi, and then I'm going to write this as 2t plus 1 to the 1/3 instead of the cube root, and then square that. Simplify that, just making the powers nicer by using laws of exponents. That's 2t plus 1 to the 2/3. Alright? And so this is all equal to area. But I'm being asked for the rate of change of area. Okay? So I have my area function of time. I need to take a time derivative. So I'm going to do dA dt. And I'm going to use Leibniz, and if you prefer, you can just say this is the derivative of area. And so this is a constant, that just stays the same. And now here, when I take this derivative, that's actually going to be a chain rule, because I'll have to multiply, I have to do the power rule first, outside, so 2/3, recopy the inside part, 2t plus 1 to the, and now I subtract 1 from the power, that's a minus 1/3, and then I have to multiply by the derivative of the inside function, which is just 2. Alright, so that's my derivative with respect to time for the area. And so now I need to, it's asking for the rate of change of the area at a specific time. So that's dA dt evaluated at t is equal to 3. And you could also write this as a prime of 3, either way. And so this is pi, and now we just substitute everything in. Times 2/3, and then let's see, this will be 7 to the minus 1/3, and then times, that's a multiply, times 2. And if you do this computation, I got approximately, we'll say this is approximately 2.2 And then now we need the units. Area is in meters, but then since we're doing a rate of change, it's going to be meters per the unit of time, which is in minutes. So this is meters per minute. All right. So chain rule, basic idea: derivative of the outside function, which is right here, times the derivative of the inside function right here. Okay. And again, remember, you may need to use multiple chains. So that's a quick rundown on the chain rule.